And welcome back, code friends and code family, to Cajun Coding. This is St. Raz, and continuing on in Python 3 with the help of the Solo Learn app and Memu emulator, we are continuing on to the map functions, the built-in functions map and filter are very useful higher order functions that operate on lists or similar objects called iterables. The function map takes a function and an iterable as arguments and returns a new iterable with the function applied to each argument. And here's an example. Define add 5x, return x plus 5, and then nums is our list, and result is going to be list map add 5 nums and prints the result. And as you can see from the result, there's been 5 added to each one of those. Okay, so what we've got here is the result. The result is going to be type is going to be a list object, and then we're using map to go through each of the items there. We're going to be adding 5, calling the add 5 function, and then we're going to be passing in an item from the nums list, and that's our result. And it says here we could have achieved the same result more easily using a lambda syntax. So here's our definition for the nums list. Result equals list map lambda x plus 5 and nums. To convert the result into a list, we used list explicitly, which is why we use the list keyword here outside the outermost set of parentheses there. We are declaring what data type our result is going to be. And it says here, fill in the blanks to multiply each item in the list by 2, and we're using a lambda syntax here. So we've got our list, our map, and this is going to be lambda right here, lambda x, our colon, this is going to be our expression here. I'm going to be multiplying by 2, and then our comma, and we're going to be passing in nums right there. The function filter filters an iterable by removing items that don't match a predicate, a function that returns a Boolean. So here what we've got our nums list, and res, presumably short for result, is going to be assigned the value. We're returning a list. We're invoking the filter function and then using the lambda to apply our rule, lambda x colon x modulo 2 equals 0. And by now that should be familiar. We're checking for evenness. So if it's even, that resolves to true. And then nums, we're going to be passing in our values from nums. And we'll be passing in each one in turn. And print res, because of the filter, it should all be our even results, 22 and 44. Like map, the result has to be explicitly converted to a list if you want to print it. And here, fill in the blanks to extract all items that are less than 5 from the list. So we've got our definition of our list here, res, we're returning a list. And what about this? What are we doing? Filter. And less than 5, our conditional check here, x less than 5. And this value, what are we passing in to this lambda expression? Each item in turn passed in from our nums list. And on to the next subject here. I'm slowing down. I'm kind of looking at some of these here. Some of these I'm familiar with, some of them I'm not. I have no idea what generators or decorators are. Recursion is an important concept in regardless of programming language. So that's something you'll encounter in any language sets. I don't know what Intertools, is that something to be used with iterables? Interesting stuff coming up. Let's go ahead and move on. Generators. Generators are a type of iterable, like lists or tuples. Unlike lists, they don't allow indexing with arbitrary indices, but they can still be iterated through with for loops. They can be created using functions and the yield statement. Yield's a keyword I haven't seen in other programming languages, so that's interesting. Here's an example. Define countdown. I equals 5 while I is greater than 0. Yield I, and then we're going to decrease I by 1. I minus equals 1. For I in countdown, print I. So this is going to be our for loop here. This while loop, what's yield? Is that going to output it? Okay. And it looks like, well, actually no, is this the print? Maybe it's creating the yield statement used to define a generator, replacing the return of a function to provide a result to its caller without destroying local variables. That's interesting. What statement is used in functions to turn them into generators? That would be yield. Looking forward to some exercises using yield. Due to the fact that they yield one item at a time, generators don't have the memory restrictions of lists. In fact, they can be infinite. I think I see what we're doing here. The generator performs a function and returns a value, but it doesn't save that value permanently in memory. It just kind of keeps going, which is probably why they named it a generator, and also why you are avoiding the memory complications of data structures that permanently store the values. So what we've got here, def infinite sevens while true, and if you just use while true, that's always going to run. That's going to be infinite loop. Yield 7 for I in infinite sevens, print I. Okay, you say this just does sevens. The ellipsis here indicates that this is going to print sevens indefinitely until the program is stopped. It's worth noting it will be until the program stops or the computer malfunctions or something like that. You're not going to encounter a memory overflow because this data is not being stored in memory. It's just being output to the console for each iteration. Well, actually, this is the loop down here. This is the definition of the generator. Generators allow you to declare a function that behaves like an iterator, and it can be used in a for loop. And it's almost as exciting as our underwear guy here. Well, these ads are killing me. Okay. Fill in the blanks to create a prime number generator that yields all prime numbers in a loop. Consider having an isPrime function already defined. Okay, so we have an isPrime function already defined, so we're not going to have to create that. So let me see. So prime number generator. So we're going to define get primes num equals 2 while true if isPrime then we're going to yield. Okay, this right here is we're going to call is prime and pass in the current value of our number, and it's going to check to see if it's prime. And if it is prime, did I misspell yield? Okay, then it is going to yield the number. And then we're going to increment the number, and in the next iteration through, it'll check to see if that's prime as well. Okay, and generators, finite generators can be converted into lists by passing them as arguments to the list function. So if you have a situation, we know that we have infinite generators where we don't have to worry about running out of memory. The generator will keep running. But if the generator is not infinite, then we may be able to save those values. And by, as it says here, by passing them as arguments to the list function. So we've got define numbers x for I in range x. If I modulo 2 equals 0, again, we're looking for evens, yield I, and then down here we're going to print this. We're going to declare it as a list, and then numbers is our function, our generator that we set up, and then we're going to pass in 11 as x here. So even numbers from 0 to 11, and we've discussed that 0 is even, so 0, 2, 4, 6, 8, 10. If we had 12, it would not display 12. It doesn't include the number itself. However, 11's odd, so it wouldn't include that anyway. Using generators results in improved performance, which is the result of the lazy on-demand generation of values, which translates to lower memory usage. Furthermore, we do not need to wait until all the elements have been generated before we start to use them. And you'll see this word lazy. Lazy indicates a function, an operation, a process that only operates when it's requested to. It doesn't go out and look for work. It doesn't act proactively. It stands by idle until a request is made of it. That's actually not a bad thing, because if you have all of your functions and operations are chomping at the bit and they're ready to do stuff and they're doing stuff before you need the stuff, it kind of slows the computer down, can slow the whole system down. There's going to be a lot of traffic. There might be network traffic if you have a distributed system. There's certainly going to be more power usage. There will be CPU clock cycles that are unavailable for other things. So lazy is not necessarily a bad thing. As they say in industry, it's lazy if you're talking about a person, but if you're talking about industry, they use the word efficiency. So what is the result of this code? Let me see. Define make word. Word, this is the empty string. We've talked about that. An empty string is double quotes followed by double quotes, and there's not even a space. A space would not be an empty string. A space is a space. So there's our word. For ch in spam, okay, word plus equals ch, and that's inside our for loop here, and yield word. And then we're going to print list make word. Okay, so let's see, make word, call that, there's the word for ch in spam, word plus spam. Oh, I see how this works. So is this going to print it 4 times because we have 4 characters here? Oh, no, it's not. We've got spam, so what we're going to do is return the S, and then we're going to add that to ch, or excuse me, we're going to add that to the word. And then we're going to have the next one, it'll be SP, and then the next iteration through, it'll add the next one, SPA, and then SPAM. So it's going to be SP, SPA. So that would be the output. And as you can see here, this is a list. So it's inside the square brackets there. And now on to decorators. That's sure to be interesting. Decorators provide a way to modify functions using other functions. This is ideal when you need to extend the functionality of functions that you don't want to modify. I see. Okay, so you have a function, there's some kind of whistle or bell that you want to add to it, but you don't want to change the function itself. You're just going to extend its capabilities for a certain purpose, but leave the function, the original version of the function, unchanged, if I'm understanding this correctly. So we've got decor, func, and then def wrap. And inside the text of wrap, what we're going to do is we're going to print this series of equals. Now this is enclosed in quotes, so this is just a string. This is just a visual thing. Okay, and then we're going to call func, and then we're going to print another series of these characters. And then we're going to return wrap. Why are we returning wrap? We'll get to that in a moment, I assume. Define print text, and it's just going to print hello world. And then we're going to assign to decorated decor print text, and then we're going to call decorated. But they don't see it actually. They don't display it executing. Let's go ahead and go to the code playground and do that. Pretty sure it's going to print hello world, and it'll have these things above and below it. And there it is. Hello world. Okay, so what we can see is this is the line that actually executes the code. Decorated. Okay, so we're calling decorated, and we're calling a function, as you can see by the parentheses. So what's that do? Decorated. We're calling decorated. What's decorated? Decorated is assigned decor, and decor calls print text. What's decor? Decor is declared up here. Okay, decor, and it takes in a function, which is print text in this case. So decor, define wrap. Okay, so we've got another function. Wrap prints this out, and then it calls the function. What's function? Func. Func is right here. Well, what's func when we called it? It was print text. So it calls print text, prints hello world. Then we're done with that line of text. We print another string of these characters, and then return wrap. This is the only part that I don't really understand. Why is it returning wrap? And I just don't know. What if we didn't return? Let's just delete this and see what it does. Okay, so it doesn't like that. None type object is not callable. I don't know. Maybe they'll cover something like that later. Doesn't seem like it would require a return value. Oh, look. They have more text here. Maybe it'll explain what's going on. See, inside decor we define a nested function named wrap. The wrap function will print a string, then call func and print another string. The decor function returns the wrap function as its result, which we know, though we're not sure why. We could say that the variable decorated is a decorated version of print text. It's print text plus something. In fact, if we wrote a useful decorator, we might want to replace print text with the decorated version altogether, so we always got our plus something version of print text. This is done by reassigning the variable that contains our function. Print text equals decor, print text, print text. Okay, I understand that, but I'm still a little fuzzy on why we have to return the wrap function. Now print text corresponds to our decorated version. Yeah. What are decorators? Functions that modify other functions, functions that return themselves, functions with an @ sign in their names. I'm going to say modify other functions, but they actually don't. Well, they do modify them. They modify the functions for the call on which they are made, but they don't change the original copy of the functions. I don't know about this return themselves. That I think that's more appropriately discussed in recursion. Actually, I do know about that. That's not the answer, but that is an interesting topic. Decorators. In our previous example, we decorated our function by replacing the variable containing the function with a wrapped version. So we've got define print text, print hello world. Print text equals, actually it's not equals assign to print text decor, passing in print text. This pattern can be used at any time to wrap any function. Python provides support to wrap a function in a decorator by prepending the function definition with a decorator name and the @ symbol. If we are defining a function, we can decorate it with the @ symbol, like @decor define print text, print hello world. And I believe that this is assuming that this decor function is defined in full somewhere else. A single function can have multiple decorators. Okay, in this one, see @decor. Okay, but we've still defined decor up here. So @decor, obviously, how would it know to put all this stuff if we didn't define it anywhere? Which statement can be used to achieve the same behavior as myfunc assign my DEC myfunc, which would be at my DEC. Okay. Oh, recursion is that close. I didn't remember exactly where it was in the lessons. Recursion is a very important concept. In functional programming, the fundamental part of recursion is self-reference. Functions calling themselves, it is used to solve problems that can be broken up into easier subproblems of the same type. A classic example of a function that is implemented recursively is the factorial function, which finds the product of all positive integers below a specified number. So the product of all positive integers below a specified number. That means the number x times 1 less than x times 2 less than x times 3 less, all the way down to 1, but not including 0, of course, because then you ruined it. Once you multiply by 0, it's 0. So let's see, for example, 5 factorial is 5 times 4 times 3 and so on, which is 120. To implement this recursively, note that 5 equals 5 times 4 bang. 4 is equal to 4 times 3 and so on. Generally, n factorial is equal to n times n minus 1 factorial. Furthermore, 1 factorial equals 1. This is known as the base case, as it can be calculated without performing any more factorials. Below is a recursive implementation of the factorial function. So define factorial x. If x equals 1, we return 1. We're finished. Otherwise, else, return x times factorial x minus 1, and then print factorial 5. Return x times factorial x minus 1. Well, we don't have factorial x minus 1 yet. So the interpreter is automatically going to call factorial on x minus 1. And that's going to ask for, when it passes in that x, it's going to ask for factorial x minus 1 from x minus 1. Well, if it doesn't have the answer there, it's going to call it again. So there's going to be repeated recursive calls to that function. So while it may take a few minutes for you to figure out, how recursion works, the fact that it does work is going to save a lot of time in terms of programming and for execution. The base case acts as the exit condition of the recursion. Eventually, while it's recursively calling this, going deeper down the rabbit hole, eventually x is going to equal 1, and so it's going to return 1. So it's going to return 1 not as the answer to your problem, I should state. It's going to return 1 to the version of the factorial function call that requested that, and then it's going to compute factorial 2, and it's going to compute factorial 3, then compute factorial 4, and so on until it gets to the original value of x. What is the base case of a recursive function? Case involving the number 1. Well, that's true for the last example, but it's not always going to be true. A case that never occurs, well, that's not going to be, that would be a null case, actually, or an empty set. A case that doesn't involve any further calls to that function, which means that the base case, the function can return a value. In a non-base case, when we're using recursion, the non-base case means that the function is not going to return a value. The function is going to have to call itself. And notice this is the longest answer here, and it's the right one. What are the odds? According to expert test takers, it's more than 33% if you have 3 options. Recursion, recursive functions can be infinite, just like infinite while loops. These often occur when you forget to implement the base case. Below is an incorrect version of the factorial function. It has no base case, so it runs until the interpreter runs out of memory and crashes. And what's so different about this? Are you spotting it? This is actually correct, but we're missing if x equals 1, which would be our base case. So without our base case, we're going to run out of memory. So I'm wondering how long this will take. Let's see. Oh, that wasn't bad. Yeah, I ran out of memory pretty quick. So okay, so what do? We remember how to do this? Okay, so if x equals 1, and I keep wanting to put a semicolon there. I shouldn't though. Oh, darn it. If x equals 1, return 1. And then here, put else. Now this is going to be in else, so we need to indent this. Okay, and this should do it. Factorial 5. If x equals 1. Invalid syntax. What did I do? Let's see. Oh, I'm sorry. We need a colon there, which is different syntax from other programming languages, and I don't use like the curly braces and stuff. So, and that's the answer. There we go. We fixed it. save that. What is the result of this code? Define sum 2x, return x plus sum 2x minus 1. So this is kind of like factorial, except we're summing instead of multiplying. Let me see. So it's 5. Is that going to be a runtime error? Because we don't really have a base case. Yeah, we don't have a base case. This is going to run into negative numbers. There's nothing stopping it from running infinitely, basically. So the theoretical result would be of this. The theoretical result would be negative infinity, because we're adding an unlimited, string of negative numbers. In reality, we're going to run out of resources, memory, or computation power. So recursion can also be indirect. One function can call a second, which then calls the first, which calls the second, and so on. This can occur with any number of functions. So if you have a function that calls itself, that's recursion. If you have a function that calls another function, which eventually results in the first function being called, then that is also recursion. And in this case, let's see, return is odd, return not is even. They're just kind of, these two functions are kind of bouncing between each other, is all that is. What is the result of this code? Define fib. Is this going to be Fibonacci? Yeah, this is the Fibonacci sequence of numbers, which is why it's fib. Define fib x. If x equals 0 or x equals 1, return x. Else, return fib x minus 1 plus fib x minus 2. And then it asks us to print fib 4. The Fibonacci sequence consists of a string of numbers. Is 0 part of the Fibonacci sequence? I'm not sure, actually. But it is the first few numbers there are 1 and 1. I'm not sure about 0. But after 1 and 1, the next Fibonacci number is the sum of the previous 2 Fibonacci numbers. So you've got 1, 1. 1 and 1 is 2. 2 and 1 is 3. 3 and 2 is 5. 5 and 3 is 8. And so on and so on. I don't recall whether 0 is part of the Fibonacci sequence, so I don't think it is. So let's see, return 1, else return. So if we do fib 4, okay, which would be 4 here, else return fib 4 minus 1 plus 4 minus 2. So that would be 3 and 2. And 3 and 2 is 5. So I think this would be 5. And that's correct. The first 2 Fibonacci numbers are 1s. Both of them are 1s. So there is no 0 in the Fibonacci sequence. Fibonacci is the name of the Italian mathematician that brought attention to this. I can't say he's the first one to discover it or anything. A lot of times that's someone lost in antiquity. So the person who gets their name on it is the one that gets the most attention for it the earliest. But sets are data structures similar to lists or dictionaries. They were created using curly braces or the set function. They share some functionality with lists, such as the use of n to check whether they contain a particular item. So we've got num set. This is Okay, so this is similar to lists and dictionaries. So this is our set, and it consists of positive integers 1 through 5. Word set equal to set spam egg sausage. Print 3 in num set. Print spam not in word set. So print 3 in num set would be actually it'd be let's see. I'm sorry. We're not outputting the integer. So print 3 in num set. Well, 3 is represented there, so it returns true. Print spam not in word set. It's right there, so it is there, but we're using our not keyword to flip the Boolean value of true to false. So to create an empty set, you must use set and then the parentheses, empty parentheses, as the empty curly braces creates an empty dictionary. So even though set uses the curly braces, if you're creating an empty set, empty curly braces would create an empty dictionary. So use the parentheses rather than the curly braces. What is the output of this code? Letters A, B, C, and D. If E not in letters, well, that's true. E is not in letters. Print 1. Otherwise print 2. But it is not in there, and we're flipping the value so it evaluates as true. So it would print 1. Sets differ from lists in several ways, but share several list operations such as len, which is length. They are unordered, which means that they can't be indexed. A set, it contains something or it doesn't contain something. It has a length but doesn't have an order. They cannot contain duplicate elements. Due to the way they're stored, it's faster to check whether an item is part of a set rather than part of a list. And I assume that is because of the way memory is handled. A list item has a presence. It's either represented or not, but it also has a location. And since set items have presence but not location, and also they cannot be duplicated, they're either there or not, that would explain why it's faster. Instead of using append to add to a set, we use add. The method remove removes a specific element from a set. Pop removes an arbitrary element. Why the heck would you want to remove an arbitrary element? Okay, so we've got our set here. I'm sorry, this is, yeah, that's a set. 1, 2, 1, 3, 1, 4, 5, 6. Print nums, and we get 1, 2, 3, 4, 5, 6. Add -7, as you can see that's added. Remove 3, and then print nums. Okay, so see 3 is here, but it's not here. One thing you note, we've got 1, 1, 1. When we print it out, we just have 1 because it is not duplicated. Basic uses of sets include membership testing and the elimination of duplicate entries. Fill in the blanks to create a set. Add the letter Z to it and print its length. So here's our set, and we enclose that in curly braces, as one does. Okay, add the letter Z, so we're going to add, and then print its length, and we use the len function. Sets can be combined using mathematical operations. The union operator combines two sets to form a new one containing terms in either. The intersection operator, which is the ampersand there, gets items only in both. The difference operator gets items in the first set but not the second. The symmetric difference operator gets items in either set but not both. And this is, you can see each of those there. First, it looks like they use the pipe there. Union operator, yeah, that's the pipe. That's not an L or a 1. The pipe in most keyboards is just above the enter key, and you have to shift to use it. It's the same key as the backslash, which is upper left to bottom right, the backslash. It's the shifted backslash key. This character is the caret. The caret is usually shift 6. In some notations, the caret is used for exponents, not in Python though. What is the output of this code? A, 1, 2, 3, B, 0, 3, 4, 5, print A and B. That would be the union. Oh, is that the union? That's the intersection, isn't it? I forgot it already. Yeah, that's the intersection. That's the intersection. So only items that exist in both sets. We've got a 3 here. 1 is only in this one. 0, 1, 2, 3 is in both. 4, 5. So it would be 3. What do we use for union? That was pipe, wasn't it? Pipe was used for union. The ampersand, the and symbol used for intersection. Data structures, as we've seen in previous lessons, Python supports the following data structures: lists, dictionaries, tuples, and sets. When to use a dictionary, we need a logical association between a key value pair. We need fast lookup for your data based on a custom key. When your data is being constantly modified, remember dictionaries are mutable. When to use the other types, use lists if you have a collection of data that does not need random access. Try to choose lists when you need a simple iterable collection that is modified frequently. Use a set if you need uniqueness for the elements, no duplication. Use tuples when your data cannot change. Tuples are entirely immutable. Dictionary keys are immutable, but values are immutable. So as a whole, dictionaries are mutable. Many times a tuple is used in combination with a dictionary. For example, a tuple might represent a key because it's immutable. Which of the following data types do not allow duplicate values? And that one would be sets. Okay, Intertools. Should we go on? I think we'll go ahead and do this. It looks like a fairly short section. We'll do this and do the quiz, and then we'll wrap up the video with the end of the section there. The module Intertools is a standard library that contains several functions that are useful in functional programming. One type of function it produces is infinite iterators. The function count counts up infinitely from a value. The function cycle infinitely iterates through an iterable, for instance a string or a list. The function repeat repeats an object either infinitely or a specific number of times. From Intertools, import count. For I in count 3, print I if I greater than or equal to 11, break. Okay, so we see when we pass into count, that's where the count starts, and it will go on forever unless we have a break condition, as we do here with 11. Fill in the blanks to import the cycle function from the Intertools. So import, wait a minute, from, actually import here. This is from. So from Intertools import cycle. There are many functions in Intertools that operate on iterables in a similar way to map and filter. Some examples: take while takes items from an iterable while a predicate function remains true. Chain contains several iterables into one long one. Accumulate returns a running total of values in an iterable. So here from Intertools import, and we can import multiples here. Accumulate, comma, take while. Nums list accumulate range 8. Print nums, print list take while. And then the lambda here, which is going to check x is less than or equal to 6. And this is going to be taking this from nums. So print nums, it'll be the whole thing, and then take while x is less than or equal to 6. Fill in the blanks to take the numbers from the list while they are even using the take while function. So from Intertools, we're going to import take while. Now we're going to use a lambda. Are we using a lambda here? Yeah, let's use a lambda. So lambda. And say we're using x while they are even. So so SAX. Oh, I'm not sure about that. This is going to be different. This is going to be list. This is where the lambda is going to be. So there's lambda, and this will be oh, I don't have focus. What happened? Take while. Did I get that right? Yeah, I did. I wasn't sure about that. So inside these parentheses is the lambda, and then this is take while. The condition inside the parentheses is true, where we have the lambda there. And while they're even, we of course use x modulo 2 equals 0. Did I miss the button? Just a little lag there. Nope. No, we don't want to close it yet. Hold on. Oh, it looks like it kicked me back out. Okay, here we go. From Intertools, import take while lambda. See if this works. Okay, come on, Solo Learn, you can do it. There we go. What is the output of this code from Intertools? Import product a equals 1, 2. Wow, okay. All right. See, range 3a. A is so A is 1, 2, product, range 3. So it'd be 3, 6, 6 length, it would be 1. Nope, that's not it. What's going on here? Let me get a hint there. It would be 6. So, see, 1, 2, range 3. So it'd be 3. The product of 3 and 2 is 6. List, it would be 6. Let me look at the comments on this one. I think some of my reasoning might be it's 6 because of the following combinations. range 0, 1, 2 value taken from num function we provided. Oh, I see. Okay, well that was kind of tricky. Okay, and it looks like we are finishing up with the Module 6 quiz. Maybe I should have stopped the lesson earlier, but we're going to go ahead and finish the quiz here. What is the result of this code? Nums, and then we have a set, nums, we have a set, we have a, let's see, nums, let's see, and nums. Okay, so we're going to reassign to the value nums the old value and then the intersection of this new set value. The ones that they have in common are 1, 2, 3. Those are the only ones. So now nums is a set 1, 2, 3. Filter lambda x, x is greater than 1. 1 is not greater than 1. So it would just be 2, 3. So nums is 2, 3. We're going to make a list out of that. And then we're going to determine the length of that list. 2, 3, there's only 2 items. So that would be 2. Okay. What is the result of this code? See, define power x, y. If y equals 0, return 1. Any number to the power of 0 is 1. Else, return x times power of x, y minus 1. Okay, and this is going to be recursive, of course. Print power to 3, so 2 to the power of 3, which should be 8. Fill in the blanks to calculate the expression x times x plus 1 using an anonymous function and call it for the number 6. And they said anonymous function because they didn't want to give it away. It's lambda. And then expression x times x plus 1, right there. And then we're going to pass in our value 6. Fill in the blanks to leave only even numbers in the list, and we've done that a few times there. Let's see, while, and then here's our lambda. Is that while? Let me see, lists. Oh, we've got to do this too. This is going to be 2. x2 equals 0. Let's see, the even numbers in the list. Would it be if? Is it while? I don't think it is. No, that's not right. But it's not if. Let me see. Leave only. So reassigning. I need a hint. What is that? Oh, it's 4. No, it's not. Oh, it's filter. That's what it is. And now, solo learn flipped out. Why is that? Oh, what happened? Oh, now we're going to get an ad. What's going on, Mimu? Oh, there we go. So, module. Hey, okay, it brought us back to it. Okay. What is it? It's filter. Gosh. How did I forget that? So, we're going to filter. And this is our lambda. That's the expression we're checking for. And we're pulling from the nums list. There we go. Drag and drop from the options below to print only the items in the set A that are not in set B. So print A, and then the second set is B. And what do we use here? We use the difference, which is the minus sign. A, they're not in set B. I think that's it. Yeah. The ones that would be in B but not in A, you'd have these switched around there. So, alright, and that gets us past functional programming. Actually, it doesn't get us past functional programming. It's introduced us to functional programming. Lots more stuff to learn, but at least we kind of know what we're doing as we go forth in practice. So, next time we pick it up with object-oriented programming. Thanks so much for tuning in this time, guys. I appreciate it. And by guys, of course, I mean guys and girls, gender-neutral guys, right? I should just say y'all. So thank y'all for visiting, and I'll see y'all next time. As always, like, subscribe, recommend the channel, comments, questions, critiques, always welcome. See you soon. Bye-bye.